Good day to all. Welcome to this lecture on Unit 2. In this video, we are going to see about the boundary conditions. So, basically, the boundary conditions are the conditions which should be met for traveling of electric field through multiple mediums. So, in order to make the electric field to be traveled in the multiple mediums, we need to have some boundary conditions that should be met in order to travel that particular electric field to across the multiple mediums. So in such a case, we are going to see about three conditions. So the three boundary conditions are to be explained here. One is between two dielectrics, and another one is between a dielectric and the conductor, and the last one is between the conductor and the free space. So these three boundary conditions are very important when we are dealing with the electric field in the multiple mediums. So as a first discussion, we are going to see about the electric field in dielectric and dielectric boundary condition. So consider interface of dielectric and another dielectric. So first dielectric is going to be epsilon 1. It is having a permittivity of epsilon 1, and the second dielectric has the permittivity of epsilon 2. So this can be defined as epsilon naught and epsilon r1, where this epsilon r1 is the relative permittivity of the first dielectric, and epsilon 2 is equal to epsilon naught into epsilon r2. So where this epsilon r2 is the relative permittivity of the second dielectric. Here we are going to apply the field in this direction, that is this is the direction of the electric field. So where we are moving our cursor. So this electric field is drawn with this vector E1 and E2, and this E1 and E2 are going to be segregated into two components. One is normal, another one is tangential component across the border of this particular dielectric medium. Similarly, we can segregate this particular E2 vector into two components, normal and the tangential component. So these two vectors are represented here as the vector addition. So these decomposed vectors are going to be taken by an finite closed path defined here. So here we have defined a closed path from A to B, C, D to A. So along this particular closed path, what are all the electric field values that are going to be met by this particular closed path. So the first one is from A to B. From A to B, it is coming along the direction of E1 T, because this particular loop is acting along the border of the dielectric 1. So E1 T is the first dielectric, the electric field in the first dielectric whose tangential component, into W, del W. Del W is the width of this particular loop minus this particular field is going to be from B to C. So from B to C, it is having two, here it is an interface is coming in between these two particular path. So in order to have that particular thing in the mind, we are having two components along this particular path. So we will be having E1 N del H by 2, because this is the sector which is having bisection between this particular interface. So we will be having this particular E1 N del H by 2 along the first dielectric. So since this particular E1 is directed along the upwards, so since we are having this particular B to C in the downward direction, we will be notifying it as a minus. So minus E1n del H by 2 plus this plus this E2n del H by 2. Also from C to D we are having minus E to T del W plus this particular path D to A. From D to A we are having two separate things to be taken into mind. So here it is coming as minus, means from here we are having the plus along the normal direction of the electric field. So we are having the two terms from here and from here. So E1n del H by 2 and E2n del H by 2. So where this ET is the magnitude of ET and the En is the magnitude of En. So from this equation we might have noticed that this particular E1n del H by 2 having the plus and minus terms, so they can be cancelled out. Also this E2n del H by 2 and E2n del H by 2 has plus and negative terms, and we can also cut those terms. So we will be having the final result as E1t minus E2t into del W is equal to 0. So we can conclude from this particular equation that E1t should be equal to E2t. So ET, that is this tangential component of an electric field along the boundaries of two dielectrics has undergo no change across the border, because those two tangential components are equal to each other. So it is said to be continuous in nature. So we can also write this particular equation in terms of flux densities. So d1t divided by epsilon 1 is equal to d2t divided by epsilon 2. Here we can notice that if these particular two terms, that is this epsilon 1 and epsilon 2, are going to change in some manner, then this dt undergoes some change across the interface, because epsilon 1 and epsilon 2 are not equal. So the terms along this particular E1 have to be changed by this particular epsilon 1 and epsilon 2 values, so that this particular d1 and d2 will also change in order to make this E1t and E2t as equal. So this dt will undergo some change across the interface. So dt is going to be discontinuous for a dielectric interface. So we have to keep in mind the electric field across the two different dielectrics are going to be continuous, but the electric flux density is not continuous, it is discontinuous. If the equation 3 is applied to the cylindrical Gaussian surface, so if you are going to take the charges which are going to be accumulated in this particular dielectrics, that is the dielectric 1 and dielectric 2, due to the application of the electric field. So we can quantify that particular accumulation of charges along this particular cylindrical volume. So if we are going to take that particular cylindrical Gaussian volume, then we can notify that this particular total charge, that is the total charge due to the particular Gauss law application. So Gauss law says that the electric flux density along the particular given Gaussian surface is equal to the particular total charge accumulated by that particular surface. So from that particular definition we can say the particular accumulated charge is equal to rho s into del s, because this is the charge density, that is the surface charge density into surface, which is going to be the total charge accumulated by that particular surface, is equal to the electric flux density into particular del s. So we are having the contribution of the particular charges along this particular dielectrics. So we will be having only two contributions along this particular del S. So that we have drawn the dash lines along this del S on the both side of this particular cylinders. So we will be having the del S along this particular side and also this side. So we will be having the equation as del d1n into ds del s minus d2n into del s. So we will be having this particular equation can be quantified as d1n minus d2n is equal to os. So d is directed along the along this particular side, because this particular d is directed from d2 to d1. So we can draw from this diagram also that this particular interface have to be notified from the direction of the d, as we can decompose this particular d1 and d2 into this particular components. So this is the direction of e1 and this is also the direction of d1. So we can notify from this particular diagram also. We can decompose this e1 and d1 as d1 and d1t and d2 as the d2t into d2n. Also we can decompose this e2 into e2t, e2n, and also this e1 as e2n and e1t. So we can notify from this particular diagram that is this d1n is going to be equal to the d2n if no free charges are placed inside this particular dielectric medium. So this free charge, that is this rho s free charge density, placed deliberately along this particular particular dielectric medium. So this have to be keep in the mind that if no free charge placed, then this particular equation is going to be applied. So if any free charge has been there, so we have to apply this particular equation. So dn is continuous, no charge across the boundary. So this equation can be written as epsilon 1 e1n is equal to epsilon 2 e2n. So from this definition, we can also define the refraction of the particular mediums. So you can take this particular diagram. Here we have notified theta 1 and theta 2 angles. So from this angle, so we can notify that e1t is equal to e1 sin theta 1, because here the angle is theta 1. So we can take triangle like this. So if it is going to be triangle, then this particular d1 can be decomposed into a sine component as d1 into sine theta 1 along this particular side. So we can say this e1t is equal to e1 sine theta 1 and also e2t as a e2 sine theta 2. So also we can take from this particular side, this is theta 1. So if you are going to segregate this particular along this axis, so if this is going to be the thing, then we can say this as the e2 sine theta 2. So also from the equation number 5, along this particular equation number 5, d1n is equal to d1 cos theta 1. So d1n is along this particular line. So if it is going to be the case, this is the sine theta and this is the cos theta side. So we can say that as the d1 cos theta 1, d2n is equal to d2 cos theta 2. So we can write this particular equation, that is d1 cos theta 1 and d2 cos theta 2 as epsilon 1 e1 cos theta 1 epsilon 2 e2 cos theta 2. So from these two equations, that is from the 7 and the 8 equation, we can write by dividing the 7 by 8. We can write this epsilon 1 will be there, e1 will be getting cancelled, sin theta 1 divided by cos theta 1 is equal to tan theta 1. So here in the denominator you will be having epsilon 1, so divided by epsilon 1. From this side we are having epsilon e2 in the numerator and the epsilon 2 e2 in the e2 cos theta 2 in the denominator. So we will be having this e2 and e2 will be getting cancelled. So from that tan theta 2 divided by epsilon 2. So we can rearrange these two equations as tan theta 1 divided by tan theta 2 is equal to epsilon 1 divided by epsilon 2. Also we can write this epsilon 1 divided by epsilon 2 as epsilon r1 divided by epsilon r2. So from this particular equation we can have a particular thing in the mind, that this particular property has come from the refraction of the light in a particular medium to the another medium. So from the if a ray is coming from the atmosphere into the water, means the ray will be getting bended along the medium of the water. So by taking that particular analogy in our mind, we can also say if an electric field is going to be traveled from one medium to another medium, that particular electric field is going to bend by some angle called, that is being defined by this particular relationship. So the bending value will be depending upon the relative permittivity of that particular medium. So this particular equation is also analogy for the particular bending of the ray in a water medium. So from this particular derivation we are having 3 points in our mind. First thing is the electric field can be traveled from one particular dielectric medium to another dielectric medium. It will be having two components. One is tangential, another one is the normal component. When an electric field is, second point is, when an electric field is going to travel from one medium to another medium, the electric field undergoes no change across the boundary, so it is continuous, but the electric flux density is going to change because this dt is a discontinuous one. Also the normal component, that is the tangential component, are only going to be changed as continuous and the discontinuous, but the normal component are equal in nature. So that is given by these two equations. So the tangential component are going to be only going to change along the electric field density and the electric flux density, but the normal components are going to be equal in nature. So refraction is going to be defined by this particular equation. So these are all the 3 points which we have to take into mind when we are considering the boundary conditions between the dielectric and dielectric boundary conditions. Next we are going to see about the conductor dielectric boundary conditions. If you are assuming a conductor, which is we are drawing here as the red mark, that conductor having the that is the sigma is the conductivity, which is going to be infinity, and also the charge along that particular conductor is equal to 0. So this condition is an ideal condition for a conductor. This is not realizable when we are considering the practical case. It may also be regard that is this condition may be somewhat realized in some materials like copper and the silver, but most of the materials having this particular condition as an ideal one, so that is not practically realizable. So if you are assuming that particular conductor having the electric field as equal to 0, because if these conditions are going to be the case, then the electric field is going to be 0. So as we have seen in the previous case of dielectric boundary conditions, the dielectric having the epsilon is equal to epsilon naught epsilon r. So also we are going to assume the same particular closed path analogy for this particular conductor dielectric boundary conditions also. So we can eventually segregate the electric field into two components as tangential and the normal component. Also the flux density also can be segregated into tangential and the normal component. So if it is going to be taken, then along the closed path, if the particular condition is going to be traveled from A to B, then it is Et into del W, and along this B to C we will be having En1 into del H by 2, En2 along the del H by 2. So if this particular direction is along this particular normal direction of the electric field, so these two cases are going to be plus in nature. And if you are going to travel from the C to D, then it is going to be minus in the tangential component side. So minus Et del W. And if you are going to travel along D to A, then it is having two terms along the negative direction of the normal component. So we will be having minus En1 del H by 2 and minus En2 into del H by 2, which is equal to 0. Also, as we have explained in the previous section also, these two terms will be getting cancelled. That is, this is positive and this is negative. Also, this is positive and this is also negative. Also, we are having the remaining terms as Et del W, and here also Et del W is there, but these two terms are negative. Also, the conductor, the electric field is going to be negative, so we are having this terms also as a negative. So Et is equal to 0. From the Gauss laws definition, we are having the total charge enclosed is equal to the electric flux density along the particular surface. So we are having a cylindrical pillbox, as we have assumed in the previous case also. We are having a cylindrical pillbox which is covering both the dielectric and the conductor mediums. So if you are going to find out the charges accumulated in a particular two mediums, we are having the accumulation of charge along the dielectric only. So the conductor having electric field of 0, we don't have any charges which are accumulated in the particular conductor. So we are having only the charges to be traveled along this particular path. So the dielectric medium is only going to have the charges. This conductor medium don't have any charges. So we can write the differential charge volume of the particular boundary. We are having dn into del s along the particular dielectric medium only. Along the particular conductor medium, we don't have any charges, so we are having 0 as the flux density value. So since E is equal to 0, so D is also equal to 0, so here 0 is coming. So this particular equation can be written as dn del q divided by del s. This is also going to be written as rho s. So from this we can conclude that 3 points: no electric field may exist within a conductor. So rho v, that is the volume charge density, is equal to 0. Electric field is equal to 0. Conductor is an equipotential body because this particular conductor has no potential difference, that is the electric field is equal to 0, so the potential difference is also going to be 0. From the equation of V is equal to minus del V, which is also equal to 0. So the potential difference is going to be 0. So the conductor is going to be considered as equipotential body. Third thing is, electric field is external to the conductor and must be normal to its surface. That is, the electric field is going to be only external. So from the battery only we are going to apply the electric field for a conductor. So by that way we are having the flow of charges inside a conductor. So if that particular case is going to be taken to the mind, the electric field is going to be external. So only the tangential component, the normal component is going to exist. The tangential components are going to be 0. So from this we can conclude this particular equation to be applied for a conductor and the dielectric medium. Also this particular boundary condition is going to be applied for electrostatic shielding of conductors. So we can make shielding of conductors, that is the shielding of conductor of this B by the conductor A from the conductor C. So if we need to shield this particular B conductor, means we are going to use this A conductor as a shield, and if you are going to make into the ground, so this particular conductor A is going to act as a shield for this particular B from the electric fields which are coming from this particular C conductor. So this boundary condition is going to be applied as application of electrostatic shielding of conductors. So next, the last thing is going to be the conductor free space boundary conditions. So we are having a free space, and in this free space we are having the tangential and the normal component of electric field, also the tangential and the normal components of electric flux. As we have seen in the previous also, we are having the conductor E vector as conductor having the electric field as 0. So free space can be defined as the having the permittivity of epsilon, which can be defined as epsilon naught into epsilon r. So this normally this particular condition, the boundary condition for this particular free space is going to be applied as the tangential component of the flux density is going to be 0, and this particular tangential component of the electric field is also going to be 0. The normal component of the particular free space and the dielectric medium is going to be is equal to the surface charge density. So from this discussion we are going to conclude that the boundary condition for the electric field along the dielectric medium, we are only going to have the normal component. Also for the dielectric and the conductor boundary conditions, we are only having the normal component, and also for the conductor free space boundary conditions also we are only having the normal component. In the conductor free space boundary conditions, the normal component is going to be equal to rho s. For the conductor dielectric boundary conditions, we are having the same boundary conditions going to be applied for this also, and for this particular case we don't have such a we are having the difference of this particular two flux densities is equal to the charges which are accumulated along the surface of the charges. So this is the conclusion we are going to need from this particular discussion. Thank you.